You'll see in the first black hole image, a dark silhouette ringed by bright light. But here's the twist. Those bright rings aren't just decoration. They're a sign of chaos. Imagine firing a laser at a black hole. Most photons either escape or get swallowed, but near the boundary between those outcomes, the fate of light becomes unimaginably sensitive. One tiny change, and the photon's path can linger around the hole for many orbits before escaping or plunging. That boundary isn't random, it has a mathematical structure tied to Lyapunov instability. So the real question isn't only why does the ring look like a ring, it's how does a black hole turn smooth geometry into a dynamical knife edge for light? Before this connection between imagery and chaos was widely appreciated, the prevailing picture of black holes' light rings came from studying null geodesics in strong gravity. General relativity tells us that light follows the curved space-time geometry, and in many cases, there exists special unstable circular photon orbits. In the idealized limit, non-rotating perfectly described by the Schwarzschild solution, you can compute these orbits exactly. The early intuition was mostly geometric. Photons can hover on a circle, but only in theory, because that orbit is unstable. Real astrophysical systems are messy, spinning, turbulent, and full of plasma. Yet the observation that the dark shadow is bordered by a bright photon ring suggested a deep link. The same unstable orbit that defines the shadow's edge might also govern the chaotic boundary between escaping and captured trajectories. Now let's zoom in on the mechanism. Consider a Schwarzschild black hole. There's a particular radius where an exact circular photon orbit exists. Unstable, meaning any perturbation grows. Place the photon slightly away from perfect tuning. If it's aimed just a bit outward, it can escape to infinity. A bit inward, it gets dragged across the horizon. Near the threshold, the photon can execute multiple near-circular loops before its instability chooses an outcome. This is where Lyapunov chaos enters. In a chaotic dynamical system, nearby trajectories separate exponentially in time, characterized by a Lyapunov exponent. For photon motion in black hole gas spacetime, you can describe the separation of two initially nearby photon paths by linearizing the equations around the unstable photon orbit. The time to separation translates into the number of orbits the photon performs before escaping or falling in. So the photon ring isn't merely a static curve, it's the visual trace of trajectories that spend increasing amounts of time hovering near that unstable circular manifold. The story deepened when researchers realized that the boundary between escape and capture isn't a simple smooth surface. It behaves like a fractal basin boundary. Follow different initial directions infinitesimally close together, and you get different numbers of loops and different endings. Each additional loop corresponds to a photon path that stayed near the unstable orbit longer, and because the instability grows exponentially, the loop count scales logarithmically with the precision of the initial condition. That scaling produces a hierarchy of increasingly narrow features in the light distribution, which when integrated along geodesics appears as a nested set of ring-like brightness patterns. In images, the earliest bright feature is a dominant ring, but theory predicts further substructure, higher-order subrings, corresponding to photons that orbit twice, 3 times, and more before reaching the observer. There's an especially vivid analogy. Think of a marble rolling on a perfectly shaped hill with a saddle point. Exactly at the saddle, it can stay balanced, but any tiny perturbation grows and sends it down one side or the other. For black holes, spacetime is the hill, the unstable photon orbit is the saddle, and the incoming photon direction is the perturbation. The photon ring is what you get when many marbles are thrown toward the saddle, and you count where they finally land after spending time near that unstable peak. Why does this matter beyond intellectual elegance? Because the black hole photon ring becomes a measurable signature of extreme gravity's dynamical instability. Observations like those from the Event Horizon Telescope don't just test, is there a black hole? They can, in principle, probe the geometry of the spacetime through the ring's location, thickness, and fine structure. If the Lyapunov exponent controls how quickly nearby photon paths diverge, then it influences how sharply the light accumulates near the ring. That means the chaotic dynamics of light are not mere complications. They're a potential diagnostic tool for mass and spin, and for departures from the simplest black hole models. In other words, chaos leaves fingerprints. It also reshapes how we think about prediction in strong gravity. In everyday systems, small uncertainties typically stay small. In the black hole photon regime, the instability amplifies uncertainty so rapidly that predicting an individual photon's path becomes practically impossible, yet the ensemble outcome, the ring, remains structured. This is a profound lesson for physics. Deterministic laws can generate effectively unpredictable trajectories while still producing precise statistical patterns. That same idea resonates across modern science, from turbulence to quantum measurement, and it supports a broader program using classical chaos as a bridge to understand what we might one day quantify in quantum gravity or in gravitational wave ringdowns. So what have we actually learned? That the photon ring is a visual outcome of photons repeatedly grazing an unstable circular orbit. That instability is governed by Lyapunov chaos. Nearby trajectories diverge exponentially, turning a mathematical saddle in spacetime into a boundary between escape and capture. And that because photons can execute different numbers of near orbits depending on their initial conditions, the ring is really a hierarchy of contributions, with the brightest parts dominated by trajectories that linger the most. The next time you see a black hole image, don't just picture a shadow. Picture a dynamical separator, an arena where light's fate becomes exponentially sensitive, and where the geometry of space-time writes chaos into the sky. If you want more deep dives into the strange mechanics behind our universe, subscribe for the next one.